Hello, and once again, welcome. This is SS Tripathi welcoming you for a new problem in organic spectroscopy. Today's topic will be on mass spectrometry, and we will not talk about the details of mass spectrometry. Instead, our today's program will be on a particular ionization technique, that is electrospray mass spectrometry, otherwise called the ESI-MS. That is a versatile method for determining molecular mass of biopolymers and synthetic polymers. Now, needless to say, this video is meant for graduate level and research level, particularly those who keep interest in biochemical research. And you know that mass spectrum is nothing but a graph of the mass per unit charge m by q or m by z and the intensity. It's nothing to do with any electromagnetic radiation. And there are several ionization techniques, and in the undergraduate level the EI technique is very popular because this is the oldest one, historically most significant, and for small molecules it is the best to give you the fragmentation patterns. So that is called a hard ionization technique. But there are many other soft ionization techniques. We will not go to the details of each technique, and I am intending to have each video dedicated to a particular type of ionization, not EI. EI is a part of mass spectrometry in undergraduate level. The CI, chemical ionization, which is very close to EI, I'll not talk about anything. I will resist my temptation to talk more about every type of ionization technique. Fab, fast atom bombardment ionization technique, SEAMS, which is very related to Fab, secondary ion mass spectrometry, MALDI, which is again a very effective technique for polymers, biopolymers, matrix assisted laser desorption ionization, MALDI. We have our next video on MALDI. APSI, atmospheric pressure chemical ionization. Don't confuse CI with APSI, it's different. We will have a program on APSI. APPI, atmospheric pressure photoionization. Then today's topic will be ESI, electrospray ionization, which has some similarity with APSI but completely different in many aspects. We shall see that. DESI, DART, LTT, LDTD, Nano ESI, these are the variations of ESI. Let's talk about the advantage of ESI-MS. For high molecular mass analytes having molecular mass in the range of kilodalton to megadalton, the mass spectrometry only suitable is either MALDI or electrospray. Electrospray has many advantages over MALDI. Of course, MALDI has its own importance. We will not undermine any kind of ionization technique. Now let me read out. They are particularly meant for the biopolymers such as protein, that is the polypeptides, nucleotides, oligosaccharides, as well as the polydispersed synthetic polymers like polyethylene oxide, polyethylene glycol, polymethyl methacrylate, and so on and so forth. Now these two terms have to be understood very clearly. One is the biopolymers, which are monodisperse, means the molecular mass is unique, a single molecular mass, that is the nature's creation. But when we prepare a polymer, that is synthetic polymer, they are polydisperse, means they have a wide distribution of molecular masses from very short chain length to very large chain length, and the intermediate chain length will be more abundant. Just like molecular velocity distribution, you have molecular mass distribution in synthetic polymers. They are called polydisperse. So we must bear this thing in mind before we take on to the application of ESI-MS in determining molecular mass of biopolymers, which are monodisperse, and synthetic polymers, which are polydisperse. It is suitable for thermally unstable and non-volatile liquids, which is the unique character of ESI. Thermally unstable biopolymers, I mean high molecular mass analytes, and non-volatile solids and liquids. It is a soft ionization technique. In fact, excepting EI, others are soft. It is an asset now in all biological labs, in biochemical research. Compatible in liquid phase because it is interfaced with high performance liquid chromatograph, that is HPLC, that column that is connected to the ionizer, that is ESI analyze, I mean ESI device, ionizer. And the molecular ion is pseudo. It is not like EI where the molecular ion is a radical cation. It's not like that. It will be added with a proton, two protons, five protons, or a sodium ion or a chloride ion. So it will be a pseudo molecular ion or quasi molecular ion in the ESI. And the important point here is that large amount of charge can be accumulated in a single macromolecular ion, and therefore Q by Z becomes very low. If Z becomes 20, if a molecule can acquire 20 plus, can you imagine what will be Q by Z? It will be very, very small. So that can accommodate, I'm sorry, this is M by Z will be very, very small. So that can accommodate the mass up to megadalton. And the most important, another important unique character of ESI, that you can measure up to femtomolar level, 10 to the power negative 15 molar concentration analyte will be sufficient for the analysis, and in microliter volume of the solution. Both positive and negative pseudomolecular ions can be created. It doesn't fragment unless otherwise you go for a tandem MS with a time of flight mass spectrum analyzer. So our discussion will be restricted to simple ESI-MS, not the tandem ESI-MS with TOF facility. In that case, you can also know some fragmentation pattern in the ESI-MS so that you can get also the structural information of biopolymers like proteins. Now the mass spectrum is very typical. It is a Gaussian, nearly Gaussian type of distribution. Near Gaussian distribution around a mid peak at the intermediate position having maximum intensity called the base peak. And for monodisperse biopolymers, the peaks are for the same molecule but with different quantity of charge. So that is a distribution of charge. That is why the different peaks are coming, but the molecule is same. But M by Z will be different because Z values are different for different quasi-molecular ions or pseudo-molecular ions. But for synthetic polymers, no extra charge can be accumulated, only +1, usually +1. So M by Z is same as M. So they will give you the peaks, give you the different molecular masses of different molecules of the same substance, same analyte, but different molecular masses. So there is a distribution of molecular masses for synthetic polymers because they are polydisperse. But for biopolymers, they are monodisperse. The peaks are due to distribution of charge, maybe positive charge, usually positive charge. We'll talk about that later. So this is the look of a ESI spectrum, always a Gaussian, near Gaussian distribution centering around the base peak, which is at the intermediate position, and the peaks go down on the right, peaks go down to the left. Now, for monodisperse biopolymers, these are due to different charges. Might be this is due to charge plus 15. We will calculate that. And here this will be maybe 16, 17, 18, 19, 20. And if this is 15, this is 14. Because as Z in the denominator increases, M, because M is fixed. For biopolymers, M is fixed. Z varies. So you get different peaks. The principle and the theory behind ESI, electrospray ionization, there are many theories have come up, but the magic, I can't say miracle, but the magic that it does, that is for sure, it's a magic, but the mechanism can be more than one. So the best mechanism, widely accepted mechanism, I am going to discuss because I have maybe 4 or 5 problems to solve so that a newcomer who is a novice in ESI-MS can understand how to approach the spectroscopic problems based on ESI. Now, the principle is I am showing you. Here is a inlet capillary of a syringe, the syringe pump. The inlet capillary which has a Taylor cone and a very, very narrow jet. And this is another outlet. This is the outlet for from the ionizer, but inlet for the mass analyzer. The molecular ion, not the molecular ion, the quasi or pseudo molecular ions will enter here to the mass analyzer. We are going to discuss about how to determine the M by Z versus the intensity graph. We are interested in this part. So a very, very high voltage is applied to these two electrodes. One electrode is the inlet capillary ending with a Z. The other one is the other capillary which is connected to the mass analyzer. So this is applied a very high voltage of the order of 2 to 6 kilovolt. Can you imagine? In such a high voltage, you can apply the positive terminal here if you want positive ions, or negative terminal here to get negative ions. That is why we have two types of ESI, positive mode and negative mode. Usually positive mode is most widely discussed in biopolymers, particularly proteins. Now when high voltage is applied, and this is the LPSA column, a pure analyte solution in a particular solvent, polar solvent, and having some acidic additive, if it is a basic protein type of substance, some additives like sodium chloride or sodium nitrate, if you want a positive ion or a negative ion. So depending on that, you add some additive, but proteins do not need any other additives than acetic acid or formic acid because they have basic nitrogen units to absorb or to abstract protons, and therefore we need only to add a little bit of formic acid or acetic acid. So the effluent from the HPLC enter into this inlet capillary at a very high, say positive voltage, and when it comes out, it produces a spray, a aerosol containing thousands and thousands of droplets, liquid droplets containing multiple biopolymers or polymers. multiple polymers with multiple positive charges or multiple negative charges. Usually negative charges are never multiple. Multiple positive charges, because many protons can be attached or abstracted by the different basic sites of a polypeptide chain having a large number of sequences of the amino acid residue. Now when these drops, I tell you the mechanism, this is called the single ion evaporation mechanism. Single ion evaporation mechanism. Now this is very, very interesting to me. Now when this is a schematic diagram to explain how the single molecular ion or the quasi-molecular ion is formed. Now when it is sprayed, this is a larger droplet. I have shown only three, hundreds of droplets having large number of biopolymers inside, not shown, and large number of positive charges, maybe 200, 500, 700. So positive charges will be there. And when it will go through the other through this space in 1 atmosphere, I forgot to tell you this is 1 atmospheric pressure, not a vacuum like EI and other techniques which need vacuum. This is 1 atmosphere. Nitrogen will be flowing in different directions to nebulize, to split the big droplets into finer droplets and to improve or to increase the flow rate. And so these droplets, after their journey, being attracted by the negative, the opposite counter electrode, being attracted by that, it is moving, and during its movement journey it evaporates. So desolvation occurs. So when solvent molecules are evaporated, the size shrinks, decreases. So this is the reduced sizes of the same droplets. And what happens now? There is a mistake here. It has been made smaller. No, this solvent evaporation reduces its size. It should have been reduced size. Yet with reduced number of analyte molecules not yet ionized, and the ions are also there, because of the positive voltage. Now these droplets not only carry the analyte molecules in large numbers, but also carry say protons in large numbers coming from the acetic acid or formic acid used, or maybe sodium ion in large numbers if sodium chloride is used, or maybe chloride ion, not sodium ion in large numbers, it's not possible. So only one sodium ion, maybe many sodium ions, no doubt about it. But let's see what happens when desolvation occurs. The number of analyte molecules decreases, as well as the number of positive charges or number of charges decreases. And when the size decreases, the positive charges, they come to the surface close to each other. So this close proximity of positive charges produces enormous repulsion, and the Coulombic repulsion becomes greater than the surface tension. So there is no way that the surface will be stable. It will undergo fission. This is called the Coulombic fission. Some people call it Coulombic explosion, but I refrain from saying that. Coulombic fission occurs, so that from that many other finer droplets come out. Smaller droplet, bigger droplet, smaller droplet due to reduction in size, not due to fission. But when it becomes smaller, then the charge becomes so enormous, then Coulombic fission occurs to produce still finer droplets containing smaller number of analyte molecules and a smaller charge, positive charge. And this cycle of evaporation, reduction in size, and Coulombic fission continues till the analyte molecule is bound to absorb the charge. Then the analyte molecule becomes charged. The charge molecular ion or the quasi-molecular ion is formed in the spray itself during its journey. Ions are there, but it will absorb, maybe it will react. If it is a nitrogen basic site, it will react to form the ammonium salt. So it will absorb the charge at such a large charge density, when it will be so small, having a lot of charges. And ultimately, when it will pass through, I am showing you, when it will pass through this heated capillary to the mass analyzer, the complete desolvation will occur. There will be no solvent molecule, only a single analyte biopolymer or a synthetic polymer, one single macromolecule with multiple charges. If it is protein, of course, if it is a non-basic or non-acidic, then say non-polar synthetic polymers, it can't carry so many positive charges. It will carry one sodium ion or one chloride ion. So there is no site. The only attachment, that is, we can call it an adduct in such cases. No real reaction between sodium ion and a synthetic polymer. We can call it an adduct, because the charge density of the droplet is so high, then the polymer is bound to attach. Maybe it reacts or attaches with an ion depending on the quality of ion present, and finally exit to the mass analyzer as a single molecule in the gaseous phase, which is required for the mass analyzer. The magnetic sector they need in the gaseous state, so they come out in the gaseous state, and a single ion with multiple positive charges if it is a protein or a basic substance. If it is a multiple acidic substance, then it will come as a negative ion. In that case, we have to apply the negative voltage here, so that negative ions, particularly if it is an acidic substance, it will lose proton. Or if someone has an acidic group which can bind with a base, then also a negative ion can be attached to a molecule having some acidic function. In that case, this terminal will be negative electrode. Now, that is the main thing of this particular process. You can read out desolvation, size contracts, fission, and finally a naked pseudomolecular ion is produced. And here the mass analyzer only sees two individual macromolecule. If it is monodisperse biopolymers, same molecule with multiple charges, plus 20, plus 15, plus 14, all. And if it is a polydisperse synthetic polymer, in that case you do not get a multiple charges, usually one charge, plus one charge or minus one charge, Na plus or Cl minus, and you have distribution of molecular masses. You get different peaks for different chain lengths. Then you can find out the number average molecular mass or mass average molecular mass later. Now, these ions are accelerated to the mass analyzer, which is a quadruple mass analyzer for simple. And of course, if it is a tandem one, it goes for another mass analyzer, which is a TOF, time of flight mass analyzer. I'll discuss about that. So, for proteins, the pseudomolecular ions could be MH plus 1 if it absorbs one proton. If it absorbs two protons, M2H 2 plus, 3 proton 3H 3 plus, 4 proton 4H 4 plus, and Z protons ZH Z plus if there's a basic biopolymers like proteins. Synthetic polymers will absorb only one sodium or one chloride, so M by Z is same as M, so that their mass measurement is not extended to megadalton, because the mass spectrometer resolution has to be high. So in that case, the range will not be that high as for biopolymers containing basic units like protein, which can absorb multiple charges. We'll see that. And in polypeptide chains, the lysine, arginine, and histidine, these are the three basic these are the three amino acid residues which have free amino group, no other. And of course, in any polypeptide chain, the free amino terminal is another one. So as many number of lysine units, arginine units, and histidine units are there, same number of proton can be at the most absorbed or abstracted, plus one free amino terminal. But not all basic sites is bound to absorb proton. It's not necessary. But the maximum possibility I'm saying. So John Vane got Nobel Prize in 2002. So let's take up how we can measure the molecular mass of a monodisperse protein molecule by which give multiple charge distribution for different peaks. If you select any two peaks, but one thing we have to assume, that is the magic. The assumption for monodisperse polymers is that any two adjacent peaks differ from each other by a single unit of charge. So let's say P1 and P2, they are any two peaks. If P1, if due to the abstraction of Z1 protons with Z1 charge may be Z1, but the mass of Z1 protons will not be exactly Z1 because the mass of proton is 1.00783 Cu or U. So we have to make a finer calculation later, but usually M plus Z1 by Z1 is the value of P1, M by Z. And for the peak left to that, or say right to that, which has got a lower charge value, will be M by Z1 by Z1. This is the P1, I have already told you. And the peak right to that, just right to that, adjacent, will be abstracting Z1 minus 1 by Z1 minus 1. For example, here Z1 is 15, here Z1 is 14. And you can also take the peak which is left to it. In that case, it will be having more charge by 1. If this is mz1 by z1, this will be mz1 plus 1 by z1 plus 1. By solving these two equations or these two equations, you can find out both the mass, monodisperse mass, and the charge of that particular peak. Now let us take an example. I have borrowed it from the University of Bristol, where these are the different peaks for a protein obtained from horse heart myoglobin. This is a horse heart myoglobin gives these peaks. Now this is the base peak, and you can take, I have selected say these two peak, 1131 and 1212, the right one peak. So for 1131, let's say m plus z by z is equal to 1131, and 1212 is m plus z minus 1 by z minus 1. So by solving these two equations, I got z is equal to 15. So this is 15. Once I get this is 15, 1131 is taken as z. If this is 15, then I simply write this has to be 14, this has to be 13, this has to be 12, this has to be 11, this has to be 10. Similarly, this has to be 16 plus 16, I mean charge. I'm not talking about the serial number, charge. So this has to be, this is 15, this is 16, this is 17, this is 18, this is 19, this is 20, this is 21, 22. So what I wanted to tell is that once you get one peak, the charge of one peak, you can find out the other peaks, because the assumption is that any two adjacent peaks, they vary in charge by 1 unit. This is 17 plus, this is 16 plus. Okay. Now I have found out 2. We have to take maybe 4 or 5 different pairs and make an average. I'm not talking about the average that we find out for synthetic polymers. I'm trying to minimize the error because the first data I found it is 16,940 Dalton, and the second pair I found 16,960. So I took the average of only 2 pairs. You have to take many more pairs so that the error will be least. So the average value of that myoglobin from horse heart is 16,950 Dalton, or 16.95 kilodalton. And in the second example, we'll be talking about a protein from hen egg white lysozyme, HEWL, where the question says that the HEWL, that is hen egg white lysozyme, has these amino acid sequences or residues in that polypeptide chain. So it has given a list of all the 20 amino acids present in different numbers. But we are interested in these 3 which contain a free amino group. This is lysine, arginine, and histidine, and there are 11 arginine units, residues, 6 lysine residues, and 1 histidine. So 11 plus 6, 17 plus 1, 18, plus the polypeptide chain has inherently one amino as amino group, free amino group, that will also abstract a proton. So the maximum number of positive charge that can be present in a quasi-molecular ion will be 19, but not all 19 can be used. In fact, a little less than that will be the highest charge. But yes, it is possible that HEWL is the last question. What is the maximum number of positive charge that can be present in hen egg white lysosome? That is 19. Because all others, each of these residues, arginine, lysine, and histidine, has one free amino. The amido group is useless. It looks like NH2, but it is not basic because of the delocalization of lone pair, So the free amino group of the entire polypeptide chain, and whenever you find these basic amino acids, RKH. So in total, maximum 19. And is asking about why there are different positive charges, because not all 19 in every analyte single molecule, single quasi-molecular ion, not all the basic sites will be observed. In some molecules 1, 2, some molecules 3, some molecules 4. So it will show a distribution of positive charges from 1 to 19. It may go to 19 or may end up at 18, doesn't matter. The maximum is 18. So that is the magic in ESI. You find everything, at least in the Gaussian region where you analyze the peaks, adjacent peaks. They are all different by 1 charge unit. That is the magic for which we are able to determine the molecular mass of biopolymers so very accurately in ESI-MS. Now coming to the third example, which we have taken from, once again, UCI, California, by Professor James Novick. And here he asks in the examination to his PhD students, a PhD level examination, that there are 2 possible tripeptide, all made up of alanine. This is alanine tripeptide structure. The pendant group, the substituent is methyl. And this is the modification that the carboxyl terminal has been modified to amide. So this is alanine tripeptide amide. This is simply alanine tripeptide. Now, the data says that the ESI-MS shows two large peaks at 231 and 253. It's a tricky question. If Professor Novick might be watching sometime, I really congratulate to have created such a tricky question. Very simple but tricky. 231 and 253. And in fact, if you add up all the atomic masses, you will find this is 231 and this is 230. But I told you that since each of the two tripeptides contain only one amino basic function, so that the maximum charge will be +1. Where is the basic function? Can you show it here? Yes, this free amino, this is the only place where proton can be abstracted, making it NH3 plus. This is amide, this is again amide, this is this is again amide. So all these are amide functions, including this. Only the free amino group will absorb or abstract one proton. So M by Z is same as M. So there will be on +1 charge, no charge distribution. So you will get only one peak, But why there are two peaks? That is the trick. Now see, the answer cannot be this one. Had it been this one, the first one, alanine tripeptide, then 231 plus 1. For proton, 1 will be added, it will be 232. But it is getting 231 in 10th peak. So undoubtedly, the alanine tripeptide amide, which has a intact molecular mass 230 plus per 1 proton here, it will be 231. So the correct answer is the amide, not the acid. I mean alanine tripeptide, right? And what is the reason for the 253 peak? Can you guess? Undoubtedly, sometimes in the solution sodium chloride impurity is there. Sometimes the scientist who performs it adds deliberately to have an extra diagnostic tool to confirm the tripeptide or the analyte. So perhaps the spectrum has been taken in presence of sodium chloride, so that 230, this is 230, this is 231, and this is 230. So 230 plus 1, 231, but had it been this case, then you would have got 232. So there is no peak at 232. A intense peak as 231. And what is the reason for 253 peak? It is due to sodium ion 230 plus 23 is 253. So whenever you find a unusual peak in peptides, you will obviously think that some other positive ion is there, metal ion is there, some other positive ion is there. So if there are polypeptides of large number of residues, not tripeptide of the same type, then you can have many more charges, positive charges, but that will be all symmetrical. You know, that will be all symmetrical. Each peak will be away from the other peak, the adjacent peak, by 1 charge unit, right? But Na plus will be only 1 charge, so it will have a separate position, not matching with this. So you can look to this odd peak, if at all there is a peak in polypeptides containing basic functions. Now let us go to our last question, again from UCI, California, by Professor James Novick. This question he set in the last November midterm examination for the PhD level students. Now, this is the alkoxide ion, a nucleophile he is using to prepare a polymer, a ring opening polymerization of an epoxide. This R dash is not known. This is a base, an ionic initiator which has been used as a nucleophile to initiate the ring opening polymerization to give a polyethylene oxide polymer. Now the question asks many things. There are two polymers which have been synthesized by taking two different nucleophile. In the polymer A, the nucleophile used is OH minus ion. But in polymer B, we have to tell that the examinee has to find out which nucleophile RO minus has been used. And for polymer A, the different peaks found are these 262.1, 305.2, 349.2, 393.2 and so on. If you have a look to the peak, it is a near Gaussian peak. This is the base peak 437.236, and to the right of this there are several peaks, and since it is a synthetic polymer and these peaks are not due to the charge distribution, different amount of charges, it is due to molecular mass distribution. Charge is always +1, and that is indirectly being hinted by this question at the final footnote, that the monoisotopic masses of protium, carbon 12, oxygen 16 and sodium 23 are this and this respectively. So from this you can guess, your suspicion is definitely this is not a basic polymer like protein, it is a non-basic, non-acidic, so we have to use sodium ion, sodium chloride, and since positive potential if you apply to this syringe, I told you in the beginning at the syringe jet, if the positive terminal is used, positive potential is used under the high voltage to 0.5 to 6 kilovolt, then sodium ion will enter into the droplets, and what will happen, how magically only one sodium ion will be observed in this case to each polymer molecule having different chain lengths. Only one sodium ion, because sodium ion is a bigger ion and there is no affinity, no attraction, no chemical reaction like the basic nitrogen functions. Here only an adduct, and once one adduct is formed, because of the reason I told you, high charge density, and it has to adsorb, we can call adsorb the ion. So that is a adduct formed with one positive ion. Second ion cannot come, it is highly improbable. So that is the case. Remember, for synthetic polymers, only the M by Z is equal to M, Z is equal to 1. So in that case, if you look to these peaks are not for different charges. All the charges are one. So these are masses, molecular masses of different chain lengths, distribution of molecular masses. And you find the difference between any two adjacent peak is same, is 44. You subtract from this from this from this, any two, you find the difference is 44. If the difference is 44, that indicates this unit CS2, CS2O, CS2, that is 14 plus 14, 28 plus 16, 44. Therefore, in both, and also the second polymer also, although the peak M by Z values are different, the molecular masses are different, but the difference is same, right? And therefore, for polymer A and polymer B, the monomer used is same, ethylene oxide. This is ethylene oxide. So the first part is over. The question has several parts. Write the structure of the epoxide, that is alkene oxide, used to make polymer A and polymer B. So this is same ethylene oxide, because the difference between the two adjacent peaks, all the adjacent peaks, anywhere you take, is 44. The nucleophile in the first polymer A is OH minus. If This is OH minus, this is OH minus, and we know this is nothing, this is H, CS2, CS2O, and you can take any pick. He is asking about 393.2 pick. In that particular pick, that represents which molecular mass, what is the degree of polymerization, how many epoxide monomer units, how many ethylene oxide units are there, what is the value of N, the degree of polymerization, or N. If this is N minus 2 and there are two more epoxy units, CS2 unit here, CS2 unit here, so the total is N. So what is the value of N? So if you look to the 393.2 peak in polymer A, this is polymer A, so this one, this is not the best pick, but this one, doesn't matter. So on trial and error, you can find that if this N minus 2 is 6, N minus 2 is 6, and this is OH, already told that the initiator is OH minus, and this is already OH is there. So N minus 2, if you take 6, then only the, and add 23. You have to add always 23 because those are all quasi or pseudo molecular ions. In all these peaks, they are not molecular masses alone. Molecular mass plus 23. Molecular mass plus 23. So all are 23 mass units more than the respective chain lengths or molecular masses. Understood? So if you add 23 and N is equal to 8, that means here it is 6 and here CS2 CS2OH CS2 CS2OH. So the total N value is 8. If that N value is 8, that means 8 minus 2, this is 6, then only it will be exactly 393.2. I have added up. I told you that it will be only one sodium. It will be an adduct, not a chemical reaction, an adduct. So there are two CS2 CS2 units for this one I'm talking of. These two. I'm talking of this one. CS2 CS2. So this is 12 plus 12, and there are 4 hydrogen. Each hydrogen is 1.00783. So for this unit, it will be 12 into 2 plus 1.00783 into 4 plus 1 oxygen is there, 15.9949, and there are 6 because N is equal to 8, so this is 6. So in this way, if you calculate and add at the end sodium is 22.9898, it is exactly coming 393.2. So it proves that N is equal to 8. And the last thing it is this is the quasi or pseudo molecular ion for which you are getting this 393.2 pick. Sodium is always be there as an adduct. That is the magic of ESI. Even if the molecule is not having basic function or acidic function, then also it will absorb a charge, positive or negative, depending on the potential that is applied to the syringe head, the ejecting spray, the jet or the syringe which is producing the spray or aerosol. Now, this last question is, what is the nucleophile used to prepare polymer B? What is the nucleophile used to make polymer B? That is the last one. And I found that all these peaks have their corresponding peaks. Now this peak 393.2 is near 363 or 407. So let us take this one. I thought possibly this is methoxide ion. Instead of OH minus ion, if he is taking methoxide ion CH3O minus to prepare another polymer B, then the extra mass will be, instead of OH, it will be OCH3, there will be 14 mass units more. So what I did, I wanted to calculate over and above 393.2, I added one CH2 unit to make it CH3. So 12 plus 2 into this, because this includes sodium. So I didn't add one more sodium. This includes sodium and only a CH2 unit. So that is 12 plus 2 point, and exactly it became 407.215. 407 point, a slight difference, in calculation and the actual experiment. So that is a degree of error. Similarly, every peak of polymer A has its corresponding peak in polymer B. The 349.183 has a corresponding peak at 363.199. 305.156 has a corresponding peak 319.173. 261.128 has a corresponding peak at 275.148. And this peak, not given its mass value, has its corresponding peak at 231.118. So also the right side, all the peaks have the corresponding peak, which are 14 units more compared to polymer A. Polymer B, therefore, the nucleophile used to initiate polymerization is methoxide ion. So this, is it not an interesting problem? So to sum up, we learned two things. We have to look to a ESI-MS in two glasses. One glass, we are dealing with biopolymers. Yes? If yes, if it is proteins, then yes, then positive, you have to go for the positive mode, and the graphs and the peaks will be a distribution of charge. Molecular masses are unique, same, monodisperse. But you are handling polydisperse synthetic polymers, then the charge is 1 always, either 1 Na plus or 1 Cl minus, as the case may be. So charge is always 1. The graphs, the peaks are for distribution of molecular masses. So the difference between the adjacent peaks will give you the repeat unit, the molecular mass, the part mass of the repeat unit, and from that you can know the entire molecular mass. And you can find out, if you get at least 5-6 values from different molecular mass of different chain lengths, you can find out the number average molecular mass, average molecular mass, or mass average molecular mass, MW bar or MN bar. I'm not going to the polymer chemistry, so that is the end. And one thing I forgot to tell you, it was not important. Every peak, here it is not so, yeah, it is shown. Every principal peak has isotope peaks, because there are so many carbon atoms in and so many nitrogen atoms in proteins. So the M+1 peak is contributed by carbon 13 and nitrogen 15. So there will be a very large number of small peaks just to the right of every principal peak. So we pay a deaf ear, no attention to these isotopics. They are of no use here. We are not going to find out the molecular formula. We are going to find out the molecular mass correctly. So this finishes our program. If you have liked it, put on the like button, and if you have not subscribed, subscribe. Bye bye. Next topic will be MALDI, matrix assisted laser desorption ionization technique. That is also a very unique method. It has got its advantages and disadvantages. Bye bye.